Well, hello everyone. Today's topic is going to be quite straightforward. It's the entropy of mixing. I'm actually making a video after a lot of days, and the reason I chose this topic is because I thought that let's have some uh, diversity. And what better diversity than to delve into thermodynamics? So, let's take a process, an isothermal process, and what is the entropy of an isothermal process? It's going to be del S or delta S is equal to n, which is the number of molecules, and k is a Boltzmann constant, ln Vf, the final volume, divided by the initial volume. So, uh, okay, let me first explain what exactly the entropy of mixing is. Actually, I assume that most of you have an idea about entropy. Most of you know the formulas. Most of you are aware of the definition. So, entropy of mixing is just, let's say we have a container and we have a gas which is A and a B. The number of molecules here should be in sub A and the number of molecules here should be in sub B. Let's say that. So the total number of molecule is going to be n equals to n sub A. N sub A plus n sub B. So let's say that we remove the partition. What is going to be the entropy of the whole mixture? That's what we're going to find out. So let's introduce a factor. Let's say Na is times n, and so b should be 1 minus xn. Okay, so tell us for a gas is we can rewrite this as this is pretty straightforward. This is just going to be phi of f vf and v. Yes, so we can just rewrite this as minus x n k ln x. We can do something similar for the B gas. So del S B, it equals to minus 1 minus x and k. Okay, I should just write it at the bottom. Okay, so and the total entropy is just going to be is their sum. So let's open a new page. Del S of mix is just going to be minus x. Sorry, not x. It's going to be nk plus 1 minus x ln 1 minus x. Okay, so this is the major formula. We have other formulas for entropies. There's another formula that I want to introduce to you guys. It's also quite straightforward. What is going to be the multiplicity of the mixture? So the total number of molecules, that's n factorial. Now these are indistinguishable, so we need to divide it by the factorial of the amount of molecules in the A gas and the B gas. So we can rewrite this as, so the entropy should be We can rewrite this as this can be generalized and be written as okay. So please excuse some mistakes that I've been making. I've been a bit clumsy. So this actually raises a question: what happens if we mix two gases that are identical? Let's say uh, two samples of hydrogen gases. So this is a this actually gives rise to a paradox, which is famously called the Gibbs paradox. I'm not going to really explain what Gibbs paradox is and go into the details, but let's say that you have hydrogen gas here and hydrogen gas there. If you remove the partition, what is going to be the change in entropy? Is it going to increase, decrease, or is it going to remain constant? The answer is it's going to remain constant. Why? Because think intuitively. What do we understand by multiplicity? What does it mean? So multiplicity is a number of uh, indis- number of distinguishable states that are different from each other. But if you mix two gases together, the same gases together, two samples of the same gases, ultimately you are just creating one entity. So the two samples of gases ultimately they translate into one gas, and you're not going to get any distinguishable states. They're going to be the same states. They're going to be indistinguishable, and the multiplicity and the entropy is not going to change. So the del S for such situation is just going to be 0. Okay, I'm going to finish my video off here. I am thinking about making more videos on thermal physics in the upcoming days, or let's say over the next few weeks. I might also make some videos on electrodynamics. So thanks for watching my video, and do comment if you have some questions, if you didn't understand any part, or if you want me to make some video on any other topic.